Hey everybody, this is Larry. This is day 29 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. And today's problem is... let's see, my neck feels a little better, by the way, in case you're wondering. Okay, 1 week. Did I click on the 1 week again? What is going on here? And today's problem is word break. Loading. Okay, given a non-empty string as in the dictionary, non-empty words, you want to segment the space, blah, blah, blah. Okay. So this seems pretty straightforward in theory. The problem is that it can have... So the problem is just try to figure out the constraint for this problem. That's what I'm thinking about. There are a couple of ways... Excuse me. There are a couple of ways to do it. There's dynamic programming, there's breadth first search, there's depth first search, and variations on between. And which one is the right answer really depends on the constraints, and it requires a little bit of mind reading because I don't know. But let's kind of do it the naive way with dynamic programming, and then we'll figure out from there. Okay. So how do you solve this as dynamic programming, right? Well, so the way to think about this as a dynamic programming problem is that let's say you have a word. In this case, you have apple, pen, apple. You can think about there's a node or vertex in between each character, right? And now, if you have all these nodes, there's an edge between two characters if the word is inside. So for example, this space that's between the before the A goes all the way to after the E because apple is a word. And similarly, this space between the A to the space after the E also has the same thing. And now that you have that, now that you kind of formulated it as a graph problem, now we can think, well, at each node, can we get to the last node, right? So basically what we're essentially answering with this question is there a way to get from the first node here to the last node? And this is, this is a problem that you could ask recursively, right? In both directions. So it depends on which way you want to do it. And what I mean by that is we ask this by, okay, is from this problem of getting from left to right, is there you could use the subproblem of here all the way to here, which is left plus 1 to right. So that's one formulation of the subproblem, or you could get it from left to right minus 1. So both of them are equivalent. You just have to choose one. In this case, it is equivalent as long as you drew the edges correctly. And that's basically how I would solve this with dynamic programming. So let's kind of start that. So dp is equal to force times n. Technically it's not n, but let's say n is the length of the string, and this is n plus 1. And yeah, and then now I'm going to do it bottoms up, though you could do it tops down if you like, just using this formulation of recursively asking the question of, can I go from left to right? And then keep on, making that interval smaller by, and this could be technically actually left plus k for some k, let's say if we go to apple, right? So we could definitely do that, and that's what we're going to do. So that means that for each slot, and what are these dp states, right? So dp sub I is equal to the node that represents the space before the ith character. So in other words, because we're using n plus 1, dp sub 0 means, for example, the node that is before all the words, the entire s. dp of 1 is the node that is before the first index character, but the second character, right? And so forth. Okay, now that we have that defined, just to be clear, now we could do a for loop of for x in range sub from 0 to, and I know that, you know, I'm just writing out explicitly, but from n to n plus 1, say. And technically, you could, it's supposed to be inclusive. You can maybe go to n plus 2, but when you're in the last node, you don't really have to ask that question. It's just default true, right? So yeah, and for me, I'm going to ask this question from the beginning, which is that, yeah, like I'm going to go from left to right, asking with whether there's a way to go from left to left plus k, meaning this version, this variation of it, right? Because this could also just be, you know, left plus k. So now we go for each word to see whether we have it. But first we have to do the base case of true for the, 0 is equal to true. Because why is this the base case? This means that we can always reach from the starting node to the starting node, which is like by definition true. In the beginning, you could start at the beginning, right? So now we just go for the words for word in word dict. If s sub x, and there are different ways to do it, but I'm just going to write s sub x. I was going to write starts with, but let's actually be a little bit more precise, which is x. Let's do k is equal to word, length of the word, and then this is x plus k, right? If this is equal to word, then that means that dp sub x plus k is equal to dbx, and this is an or equal to, right? Or maybe another way to put it, just to be more precise, is if this is true and dp sub x is true. And then at the very end, we can just return whether dp sub n is true. And I'm going to do a couple of minor optimizations just because it pains me a little bit not to do them. Even though this should be right, and you know, it's just performance. And I advocate not caring about premature optimization until you get more familiar with it. But it just bothers me a little bit. And one is that, okay, when we look at all this recurrence, if dp sub x is false, this would never be true, right? So that, so that means that we don't have to care about this loop if dp is false. So if not dp sub x, we could continue. And then now that means that we could factor this out, and we know that dp sub x is true, so we could just say this is true. Another optimization you can do is just pre-cache the length of each word, but I think I'm okay for now. So let's run this code real quick. Looks good. I think there's some base cases with empty strings or something like that. The dictionary gonna do okay. Okay. And that should be it. Let's give it a submit. Maybe I have some edge cases, but I'm okay with that. Okay, so that's good. So what is the complexity of this, right? So because of the language that I use, there is some nuance in how to determine the running time complexity. And maybe if I had done it in top down, it would be easier to see. But I don't know. I think I keep on solving stuff top down, so it's good practice for me to get back into doing things bottoms up. But let's do the space complexity first, right? And the space complexity should be straightforward. We look at dp as equal to this linear array. So linear complexity, space complexity is linear in the size of S, right? And in the space, we don't really care about the dictionary at all. And then time complexity is a little bit complicated, right? Because we do it bottoms up, we can count the loops a little bit. And here we see that, you know, we do O of n iteration, outer iteration. We have O of W, let's just say, for the number of words in the inner iteration. And the thing is that this actually costs stuff as well, right? This costs k. So, and what is k? Well, k could at worst be n. So for each inner the work that is done per inner iteration, and for the string comparison, right? And in that case, then in this, and if you just multiply them all together, because for each you can say it aloud using English, which is why this is easier. For each outer iteration, there's W inner iterations, so it's n times W. And then for each of those loops, you do O of n work. So combined, it is O of n squared times W. Cool. So that's all. So that's the space complex. Oh, sorry, that's the time complexity. This is dynamic programming. You could have also done breadth first search, depth first search. Maybe play around with those ideas. Depth first search with memorization, perhaps. Yeah. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and I will see y'all tomorrow. Bye bye.